Stripping down science. The Naked Scientists.
Hello, it is Sunday, December the 5th. Welcome to The Naked Scientists with me, Chris Smith.
And me, Diana O'Carroll.
Well, this week we're looking at new ways to generate, store and distribute electricity, including a system that stores energy at minus 160 degrees Celsius.
We'll also hear how energy kiosks are set to spring up across Africa to take portable electricity to remote communities.
And in the news, why young people are more likely to fall victim to the flu and how a dose of worms controlled a man's inflammatory bowel disease.
And on the subject of bowels, I'll be getting to the bottom of this intriguing question of the week.
Given that people can absorb medication in the form of suppositories, is it possible to absorb enough water to survive through their bottom?
So keep your friends close and your enemas closer. Chris?
I thought you were going to say friend or enema, actually, because that's who goes there. Anyway, if you've got any other questions for us, we would love to hear from those. You can contact us through Twitter. You tweet at Naked Scientists or write on our Facebook page. You can get there by going to nakedscientist.com/Facebook, or you can drop us an email. The email address for the programme is chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
You're listening to The Naked Scientists with Chris Smith and with Diana O'Carroll. First up, let's take a look at some of this week's biggest science breakthroughs. Diana.
Well, this week, researchers in Buenos Aires and Nashville have come one step closer to finding out why it is that those members of a population who should be the fittest, i.e. young and middle-aged adults, are the most likely to die during a pandemic flu outbreak. The most recent lot of flu to receive media attention was in 2009 with H1N1 or swine flu. It killed 17,000 people worldwide during its peak. And Fernando Pollack and colleagues found that the elderly were spared the worst of this outbreak and that the very young suffered a much milder form of the disease than the adults.
When you say they found that, how was this just looking at the numbers?
Yeah, this was looking at the numbers and looking at reports by hospitals. And they suggest that the killer of these young and middle-aged adults was their own immune system. The researchers took sections of the lungs of the victims of the 2009 pandemic and found that their lung tissues were inflamed, they were heavily damaged, they had traces of H1N1, but they had huge amounts of the biomarker C4D. Now, C4D is a byproduct of the body's immune response, so it's a really good indicator of how vigorously your body is fighting an infection. These researchers also looked through some lung sections of the victims of a previous H1N1 pandemic in 1957, and from these aged samples they again found evidence of a strong immune response. What they think is happening is that the immune system in these individuals mounts a response based upon its knowledge of bog-standard seasonal flu, and this immune response is ineffective against H1N1, but it is vigorous, and so it ends up killing the patient. The researchers hypothesised that the elderly escaped because they were exposed to the previous pandemic in 1957, and they think that the young escaped because their immune systems just haven't been trained by ordinary seasonal flu. So the next step is to find out who has the immune system which is most likely to overreact in this way to pandemic flu, and the authors think that genetic testing will be key.
It's paradoxical, isn't it, that the people that come off worst are the ones that have actually had flu before, but not long enough ago to have had the form that turns out to be the nasty one.
I know, it seems terribly unfair, but they've got the best immune systems but have just been trained in the wrong way.
And you say that the next step forward is to do some genetic testing. Do you mean as in to genetically test the people to see if there are vulnerable parties, or whether it's a question of seeing if they've got antibodies on board that might make them vulnerable and therefore giving them a vaccine rather than a dose of the flu?
I think it's to identify those ones that have the immunity to the certain types of flu, yes, and those which have the strongest immune systems.
Certainly a fearsome illness, the flu, and it's already circulating quite early this winter. We're seeing cases of both flu A and flu B in hospitals here in the UK and also over in America, so it seems to have come a bit earlier this year. Let's hope we're not going to get a bad year. Well, from That top half of the body down to the bottom half of the body now. Mara Broadhurst is a researcher at the University of California, San Francisco, and she and her colleagues have got a paper in the journal Science Translational Medicine this week which documents the case of a 35-year-old man who has taken medicine into his own hands and actually into his own bowels to treat a problem called ulcerative colitis. And ulcerative colitis is an example of a disease spectrum called inflammatory bowel disease, and this is where the immune system relentlessly attacks the lining of the intestine. In the case of ulcerative colitis, it's the colon, the large bowel, that comes under attack, and no one really understands exactly why this happens. It could be that the immune system is reacting against bacteria which are present on the lining of the bowel, and for some reason some people react more vigorously than they should, and this inflames the bowel. But for people who get this disease, which is quite common, it causes severe bloody diarrhea. It can therefore cause constitutional symptoms. People lose weight, they feel very unwell, you get very severe abdominal pain, and it can also lead to bowel cancer in the long run if it's untreated. Now, the treatment is both medical. You can give drugs and things to damp down the immune system, but sometimes this treatment fails, and often the one remaining option is for the patient to undergo a colectomy, a removal of at least part of the bowel that's affected by the disease. There is another possibility, though, because if you look across the world, you'll see that where people tend to be most colonised with parasites, in other words, worms, you see the lowest rates of autoimmune disease, examples of the immune system turning on your own body, and allergy. And the hypothesis is that perhaps these parasites are in some way secreting something into the bowel which controls the immune system. Now, that's logical because something's got to stop the parasite from being rejected or ejected from the body. So clearly there are things coming out of things that live inside you to stop you attacking them. But one possibility is that these effects also prevent the body from injuring its own tissue. And in the paper in question, this 35-year-old patient who had very bad ulcerative colitis was offered the option of undergoing a colectomy, and he declined and instead elected to feed himself 1,500 roundworm eggs from a human strain of roundworms, Trichuris trichuria. And this particular strain of roundworms natively colonise human guts, and they live inside the intestine and they feed off what you eat. And almost immediately after he took this dose of worm eggs, this patient's symptoms improved. And the doctors who were looking after him were in this very privileged position because they could go in and look and compare how the bowel changed before he took the worms and after the worms got established, and then follow him up. And for 3 years he remained extremely well. He had a bit of a relapse, and tests showed that the number of worm eggs he was excreting had dropped down, suggesting the number of worms inside him was dropping. So the patient then reinfected himself with another 2,000 eggs, and again his symptoms completely resolved, and again the doctors were able to go in and take samples from the lining of the bowel. And what they found over time by studying this time course is that when the worms are present, they make the immune system flock to the lining of the bowel and secrete a number of factors, including one called IL-22, which is an important immune signal that seems to do a number of things. One is it encourages the bowel lining to grow more. So because it's proliferating more, it heals better. It also encourages the bowel lining to produce more mucus. The idea being that this would help the worm to be ejected, but it has the secondary side effect of protecting the bowel lining from whatever is causing the irritation that leads to ulcerative colitis. So this is the first time anyone's got a really clear time course, biochemically, genetically, and in terms of actual response to therapy with worms in this kind of context. And so this is the first time we've actually got an insight into how you might be able to maybe use this strategy to inform treatments in the future.
Right, but I'm guessing that most people don't want to eat a handful of worm eggs. So can you actually make fake worm eggs to solve this problem?
Well, the worms don't just stay as eggs, because the worm eggs actually hatch and they turn into mature adult worms that then live inside the intestine. So the idea is to use this kind of study to inform a strategy so we can develop a pseudo worm or a fake worm, or whatever agents the worm secretes. You just put those into the person and they then get all the benefits of having the worms without having to infest themselves, which is a good thing, I guess.
I think so.
Well, also this week, a team from Arizona State University have announced the discovery of bacteria that can thrive in an environment laced with arsenic. This is a chemical that's normally very toxic, but not only can these bacteria tolerate it, they can even use arsenic instead of phosphorus, which is normally a critical element in DNA. And Professor Paul Davis from Arizona State University is one of the authors on that paper. which announces the discovery this week in Science, and he's with us now. Hello, Paul.
Hello, welcome from Arizona.
Thank you. First of all, what actually is the bacterium that you've been studying, and how did you come to isolate it?
It's a common or garden bacterium. It's not a weirdo. It didn't stand out as being anything odd. And if it wasn't for the brilliant insight of my colleague Felisa Wolf-Simon, who incidentally is now working at the U.S. Geological Survey in Menlo Park, then we would never have known that there was any amazing arsenic capabilities. But she had the hunch some years ago, which we then developed here at ASU into a full hypothesis. So there could be organisms that can replace phosphorus with arsenic. These would be, as it were, arsenic life. And she went to look for them in Mono Lake in California, which is heavily contaminated with arsenic. So it was a shrewd place to look, but we would never have known if she hadn't fed them on a diet with huge amounts of arsenic and zero phosphorus.
So what happened was she initially got the samples of bacteria from the lake, which are tolerating a degree of arsenic in the environment, and then by forcing them to live in an environment that's very arsenic-rich with no phosphorus, they were able to substitute arsenic into their actual behaviour biochemically in terms of DNA, lipids and everything else that keeps their cells going, and use arsenic in place of phosphorus.
Absolutely right. They took the arsenic into their vital innards. This was an important point. Of course, ideally, we wanted to go somewhere where there was much more arsenic and much less phosphorus. And there are places on Earth like deep ocean volcanic vents, but they're expensive to get to. Mono Lake is convenient, and also there's been work done there by Ron Ormland at the U.S. Geological Survey studying organisms that flirt with arsenic, but nobody other than Felisa and a handful of us had really expected to find anything that did more than that flirtation, that would actually take the arsenic into their innards and use it to substitute the phosphorus. And so this is a first, because all along biologists have assumed that all life is built out of the basic toolkit of 6 elements: carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur. And here we have an organism that departs from that basic toolkit.
Chemically, why is it possible for this bacterium to substitute arsenic for this, what we previously thought of as absolutely critical element, phosphorus?
Well, arsenic is a poison precisely because it looks chemically like phosphorus, and so that's the reason that led us to think that this might happen. But we don't understand the mechanism. We don't know who's shifting the gears inside these little bugs, what actually is going on. All we can tell is that the phosphorus is getting replaced by the arsenic. Ideally, of course, we'd like to find an organism that right from the outset is arsenic through and through, and for which phosphorus is a poison. This is not it. This has dual capability. It likes phosphorus, it likes arsenic, it can deal with both, and so it can sort of mix and match. But the holy grail would be to find one that was an arsenic organism by obligation, not by choice.
But I think the point is, and the point you make very well in your paper, is that this shows that if we complacently think that all life has to be based around these 6 building blocks that you've mentioned, one of them being phosphorus, actually this is not true, and we have an example here on Earth of how an organism can substitute a completely different element into its life, and therefore this suggests that the opportunities for life to exist in an entirely different way than the way we understand here on Earth could well exist in outer space.
That's right. Well, not perhaps outer space, but on a planet or moon that was rich in arsenic. But I think it proves an even more exciting point, and that is that you could have radically alternative forms of life hiding in plain sight right under our noses, just looking like any common or garden microbes. You can't tell by looking with microbes what they're made of, what makes them tick. And this study is part of a broader context to look for what we call a shadow biosphere, or the search to see whether Earth hosts more than one fundamentally different form of life. That is there just one tree of life with lots of interesting branches, or might there be more than one tree? Now, this particular organism is clearly on the same tree of life as you and me, but it does show, because you can't tell by looking, that there may be even bigger surprises in store. And if we follow the arsenic, see where that goes, we might find that we have an organism which simply can't even be fitted on the same tree of life as you and me, and that would show that life on Earth has started more than once, and the implications of that are literally cosmic.
I was going to say that the life we see on Earth today is life which is adapted to the planet as it is now. If we were to wind the clock back 4.5 billion years to the very early Earth, it was a very different place. It's possible that there were organisms like this abounding, and they were replaced by the ones that suit the planet as it is today.
Yes, the more conservative interpretation of this is that this is a sort of latter-day adaptation to tolerate high arsenic conditions. But the more exciting possibility, as you mentioned, is that maybe life started out going down the arsenic route for the simple reason that the favourite place among astrobiologists for life to begin are the deep ocean volcanic trenches, where there's a sort of chemical brew being stirred around by the heat of the volcano. And if that's the case, well, it's laced in arsenic down there. It's a very arsenic-rich environment, and so it makes sense to think that maybe life started out with arsenic, and only when it spread did it start making use of phosphorus. So these things could be like living fossils, a hangover from those ancient days. It's too soon to say yet, because we need other examples. If we have a whole collection of arsenic microbes, we can begin to do a phylogenetic tree. We can begin to see how ancient they are, how ancient the genes are. But it's early days yet.
And just to finish us off, Paul, you've done this for arsenic, but what about the other elements that we know are critical for life? Is it possible that other neighbours in the periodic table of elements that are, again, chemically similar in the same way that arsenic is to phosphorus could be substituted in life, and therefore we have other organisms that are using entirely different chemicals instead of those carbon, hydrogen, nitrogen, oxygen, sulphur, phosphorus?
Well, it's rash to rule anything out in this game, of course. The favourite is carbon being replaced by silicon, and that's so popular it even made it to an episode of Star Trek. So we have to take it seriously. But my chemist friends tell me that that's a pretty tough one, and I think carbon would be the last to go. But we do have to take a look, say, at sulphur, and also the possibility of the fact that possibly phosphorus could be replaced by something other than arsenic. So I think this is going to open the eyes of microbiologists and encourage people to look in a much wider range of locations and a much wider suite of chemistry than we have dealt with hitherto.
Should always take Star Trek seriously. Paul, thank you very much. That's Paul Davis from Arizona State University. Diana.
Well, also this week, researchers in Nashville have found that the season in which mice are born can dramatically affect how their body clocks work in later life. Mice born in the summertime were better at adapting their body clocks to night-day changes than those born in the winter. Publishing this week in Nature Neuroscience, Douglas McMahon and colleagues reared mice in artificially engineered seasons. Some were raised with more daylight, emulating summer, and some were exposed to more nighttime as they grow up. Another subsection of the mice were then exposed to a different season during adolescence, and finally, once they reached adulthood, all of the mice were put into darkness so that the researchers could observe how they scheduled their activities. Now, the winter mice in this environment slowed all their activities, whereas the summer mice maintained a regular day-night cycle. So the researchers think that the circadian rhythm is actually imprinted on the brain during a key period during the mouse's development. And they also say that a strikingly similar response is present in people who suffer from SAD, or seasonal affective disorder. So I suppose the next step in solving this will be to find out exactly when this seasonal imprinting occurs.
So are they saying that people who have seasonal affective disorder are more likely to have been born in the winter, in the darkness as well?
Yeah, I mean, it's interesting because a few years ago Richard Wiseman did a study to find out if summertime babies ended up being more optimistic or pessimistic than wintertime babies, and actually it turned out that, yeah, summer people like me are much happier and optimistic than winter people.
Well, there are a number of different neuropsychiatric conditions that are more common in people who are born in the winter, including schizophrenia and depression. And so that would sort of fit, because we know these things are also very strongly linked to the body clock as well. If the body clock goes wrong, many of these conditions get worse.
It's true.
Well, I was born in January, so I wonder what that says about the way my body clock works. It might explain a lot, actually. Now, also this week, a group of scientists have found a way potentially to treat chronic pain. There's a paper in the journal Science. It's by Zhangyao Li, who's at the University of Toronto. And what this team have done is to study mice in which they've made a ligation injury, in other words, tied a bit of suture material around the common peroneal nerve, which supplies the limb. And this induces a pain state in the mice, a bit similar to a human condition called allodynia, which is where you get inappropriate sensitization of a patch of tissue, where if you touch that tissue and just stroke the skin gently, what should be an innocuous stimulus is interpreted as excruciatingly painful, and you get this chronic pain sensation. Now, they were working in mice that had been genetically modified so that they made green fluorescent protein, this jellyfish gene that glows green, in cells that react to nerve injury. And when they looked through the nervous system in these mice that they made this injury in, they also noticed that some of the cells in the front part of the brain called the anterior cingulate cortex, which connects the more primitive areas of the brain to the higher executive centres, the prefrontal cortex, they found nerve cells glowing there, indicating there was some kind of reaction in that part of the brain to the nerve injury. And they reasoned that perhaps this might be part of the way in which consciousness is informed of the chronic pain state. So they wondered whether if you rewrite the nerve connections there or erase the memory of the pain in that part of the brain, perhaps that will make the pain go away. So they used a chemical which is called ZIP. Now this stands for zeta pseudosubstrate inhibitory peptide, that's why it's called ZIP, and it inhibits an enzyme which is called phosphokinase M zeta. And phosphokinase M, scientists have found in recent years, is crucial to strengthening the connections called synapses between nerve cells. So when you have this PKM zeta enzyme present in the synapse, it recruits receptors for the nerve transmitter chemical to that synapse and makes them remain strong so that the signal is amplified across the synapse effectively. If you inhibit that enzyme, then the connection is weakened, and if you apply that to the memory parts of the brain, you can actually erase whole memories by injecting this ZIP chemical. So what they did was to take their mice that had this allodynia, they then introduced some of this ZIP chemical into the anterior cingulate cortex where they'd seen the glowing green cells, and the mice went back to being normal. The pain was forgotten. So it suggests that some of these chronic pain states, which are very common in humans, could be partly a memory in the brain, and that erasing that memory, and discreetly just that memory by focusing on the bit of the brain harbouring that pathological memory, could be a way of preventing people from suffering for long periods of time from these sorts of relentless pain states.
Sounds a little bit Total Recall, doesn't it? But how long does this effect last?
Well, because you're deleting connections between nerve cells by inhibiting this enzyme that maintains the strength of those nerve connections, then the connection is lost forever, and therefore the memory is erased permanently. And if you teach mice something and then inject this into the part of the brain that is involved in them learning whatever you've taught them, you can actually erase discreetly just that memory. So the answer is it would be forever.
So maybe it could even be used for something like PTSD, post-traumatic stress disorder.
Well, actually, yes, you're quite right. It could be. And they've actually been looking at precisely that problem, looking at pathological memories and other things to see if you could actually erase bad memories, because although you're erasing the memory, you're not damaging the brain or its ability to form new memories. So you just discreetly remove the bad ones and leave everything else intact, and the ability to form new ones intact too.
Fascinating stuff. And if you want to find out more about these stories, you can find them on our website, and that's at thenakedscientists.com/news.
Keeping you abreast of the world's best science. The Naked Scientists. For more information, look us up online at nakedscientists.com.
This is The Naked Scientists with Chris Smith and with Diana O'Carroll. Now, coming up, we've got in store for you new ways to generate, store and distribute electricity.
But first, for this week's episode of Planet Earth, Richard Hollingham has scurried off to the University of Leeds, yay, my hometown, to meet ant researcher Bill Hughes.
These are dinosaur ants from Brazil. They're one of the largest species of ants in the world. They're about 3.5 or so centimetres long. They have a pretty powerful sting on them, as you'd guess from looking at them, considerably more painful than a bee sting. They're interesting because, unlike most ants, which have queens and worker castes, as you probably know, these are what we call primitively eusocial. They have an alpha-female, beta-female dominance hierarchy, so they're actually very, very similar to our vertebrate societies, wolf packs, meerkat packs, things like that.
So you could compare these to a much higher animal, like a wolf, for example.
Absolutely. And in terms of the social interactions within the societies, they're very, very similar. The beauty of them from research, of course, is that we can have multiple colonies of these ants here in this relatively small room, whereas if you were trying to do the same kind of experiments with a wolf pack, you obviously couldn't.
They do look almost prehistoric, don't they, with a long pointed abdomen, almost like a wasp, a head with these pincers at the top and these long legs out at the side, and then these long antennae as well, which are moving around.
The ants evolved from wasps, and so you tend to find that the most primitive species of ants are very wasp-like in behaviour and also in morphology. Yeah.
Now, these are known as social insects, but what you're looking at is the fact that they're not always that social. They can be antisocial.
Yeah, that's right. I mean, when we look at a social insect colony, in fact, just as when we look at a human society, it's obviously the cooperation that's the most obvious characteristic. It seems that the society is very egalitarian. As we've started looking in more detail at social insect societies, though, we find out there's actually an awful lot of conflict within them, because individuals aren't clones of one another, they're not reproductively identical, and so their interests differ to a greater or lesser extent. For example, in these dinosaur ants, okay, we have an alpha female, a beta female, and so on, a dominance hierarchy. But because they are morphologically the same, there's a lot of potential for subordinate females to try and reproduce, and they do that. They'll lay eggs. The alpha female will normally detect the egg and will police it by cannibalizing it. In fact, the alpha female is particularly clever because rather than just using physical aggression to exert her dominance, like in a wolf pack, she actually uses chemical cues to do it. So if she detects that a subordinate female is challenging her, she will smear that individual with the venom from her sting. She doesn't sting the subordinate, she smears it with venom, and that acts as a signal which causes the other individuals in the colony to act aggressively towards that challenger and to spread eagle the challenger. So she's really quite clever. Rather than enforcing her dominance herself, she uses the other individuals in the colonies to do it.
Okay, so you've got these dinosaur ants which have been around for, 100 million years or so, but you've got more recent ants in here, leafcutter ants.
Yeah, so these leaf-cutting ants show a much more advanced form of sociality than we see in the dinosaur ants. But you can see they've got tiny, tiny workers, much larger workers, and then the queen is huge. So a larva, when it's developing, they may develop into a worker or they may develop into a queen. And theoretically, they're all meant to have an equal chance. It's turned out, though, when we've used genetic methods to look at the kind of dynamics within them, that it's not actually equal, and that individuals which are the offspring of some fathers have more chance of becoming a queen than others. So they're essentially cheating their nestmates out of their fair chance of becoming royalty. And one of the obvious explanations might be that there's some form of nepotism going on, because these maggot-like larvae are being reared by adult workers. Maybe if the adult workers are able to recognise the larvae that they're more related to, they could preferentially care for them. Theoretically, that shouldn't occur. We've just been looking at these recognition cues, which these ants have on their cuticles, and we found that actually there is the information there to allow individuals to recognise their kin. So it's one of those examples where we had a very strong prediction from theory, but when we've actually been able to use very advanced chemical and genetic techniques in combination, it turns out that actually the information is there. So it may be that they don't use that information, we still have to find that out, or it may be that they do, and possibly that explains this form of royal cheating that we see going on in these colonies.
Bill Hughes from the University of Leeds talking to Richard Hollingham. You can download the latest Planet Earth podcast as well as find links to Planet Earth online on our website at thenakedscientists.com/Planet Earth.
Thank you very much, Diana. And if you'd like to get in touch with us here on the programme, it's chris@thenakedscientists.com.
Now, across the developed world, we tend to take it for granted that we can simply plug in a kettle or a computer and there's electricity on tap. But in many parts of the world, this simply isn't an option. Much of rural Africa is off-grid. And as electricity grids are expensive to build and maintain, in places where they do exist, the electricity can be prohibitively expensive. But Mira Senthilingam has been to find out about a new and surprisingly simple solution which is being pioneered here in the UK to take affordable power to those that need it.
Rural electrification is one of the biggest challenges facing the developing world, with billions of people worldwide living without access to electricity. Countries such as Rwanda have tried to tackle the problem by increasing access to the grid, but due to expense, maintenance and infrastructural challenges, the problem still remains. As Rwandan local Simon Bataringaya explains.
Electricity is a big problem in Rwanda. Lightning around is a big problem. Security problems comes up with it. Hours of working are limited due to that short period of time of lightning. According to the figures, the census that was made towards the end of 2009, 7% of the population of Rwanda have access to electricity. More than 90% of the population of Rwanda lives in rural areas. For those, only 0.1 have access to electricity. And to be quite clear, the total number of the population is more than 10 million. So electricity is still a problem to Rwanda, which limits the development.
Simon Bataringaya in Rwanda. Currently, residents of Rwanda overcome these limitations by burning kerosene and candles to provide light, as well as paying to use generators at markets. But now, a team of engineering students from Imperial College London have developed the project Equinox, solar-powered energy kiosks located in rural areas that charge and provide battery packs to locals. The first kiosk was located in the district of Minazi, with another updated design opening in the district of Bugesera. Vice-Chairman of Equinox, Daniel Chowdhury, explains more.
The energy kiosk concept is a centralized charging station. The latest solar kiosk has 10 solar panels on the roof. Simply put, the solar panels will charge these battery boxes. People will take them away once they've used it for various applications, whether it's lighting, charging their mobile phones or radios. They'll bring them back, and the energy kiosk will charge it back. Solar panels are wired through charge controllers. Then they reach a large storage battery. What this allows is that if you have rainy days or foggy days and you don't have enough sunshine, it provides a source of backup power.
Now, you have examples of battery boxes in front of us, starting with the original box and also the current box that's being used. The main difference I see between them is the size. Tell me a bit more about the actual battery boxes.
So the original battery box is 12 ampere hours in size, and the new one is about half that size, 5 ampere hours. The old one provides 12 volts of DC supply, and the new one provides 230 volts through an inverter, which is included inside the box. What this means is that the new box is basically a portable plug, so you can plug in just about anything that's generally low-powered. So whether that's your mobile phone charger or simply the lamp we provide, it'll be able to power it.
So the setup in Bugesera, as you mentioned, how many battery boxes are provided there and how much power is generated as a whole?
The Bugesera solar kiosk has 10 solar panels, which are 65 watt peak each, and we serve 120 households using our battery boxes.
It all is largely kept going by the fact that you charge a fee to users. So what is this fee and how was that actually set?
People will pay an initial deposit of about £10 and a £2 monthly recurring fee to charge the battery boxes. The money generated is used to pay for the shopkeeper, for maintenance costs within the kiosk. We based this price on kerosene and people's kerosene usage so that it doesn't add up on their costs, but replaces the cost for buying kerosene for the energy needs. So while kerosene can be used for lighting, our battery boxes provide an additional service of, say, charging your phones. Everyone has 2 mobile phones, and the network is sufficient there. But they just need a point to charge their phones.
Daniel Chowdhury, Vice-Chairman of Equinox Energy Kiosks. The technology Daniel mentioned, however, isn't limited to solar power, as the team have recently adapted the design to tap into other renewable energy sources, as well as tap into the grid. Chairman Christopher Hopper told me more.
At first it might seem kind of counterintuitive. Why do people by the grid need battery boxes? They have the grid. But the fact is that quite a lot of people don't have access to grid even though they live close. In fact, some people live under a grid line and they live in the dark after 6 o'clock. There's 2 main reasons for that. Number 1, often people can't afford the grid connection. Number 2, some people could afford it, but they live too far away from the grid, as in close but not close enough to be connected. So we think that by putting grid-connected battery charging stations along the grid, you can kind of extend the reach of the grid.
But as well as these main sources of energy, you're also now exploring the potential of hydropower in the future.
We want to rather develop a flexible solution. The energy kiosk is a flexible solution for electrification. So particularly Rwanda has a lot of hydropower potential. It's a very hilly country. In fact, it's called Land of 1,000 Hills. Quite a lot of rain as well. So there's many little rivers that you can make use of. When I talk about hydropower, I don't talk about huge dams or big power plants, but rather really, really small scale hydro generation, pico hydro. So a couple 100 watts of continuous power would be enough to power a small community. What's particularly attractive is that hydro gives you round-the-clock power. So if you combine that with a buffer battery, for example, you can really charge a lot of small battery boxes to cater to local demand. So basically, if you compare it to a solar-powered kiosk, for example, in Bugesera, we have 650 watts solar power installed. 100 watts of continuous hydropower would be the equivalent to power a similar-sized community.
And providing this portable power by manipulating different methods of energy generation could pave the way for the future of all rural electrification.
The classical way of grid electrification doesn't really work. Just like people in Africa, or a big part of the continent, just skipped the whole landline connection for telephones. We think, this battery box concept can be the equivalent of mobile phones in power distribution, because it's a much more flexible solution than, hardwiring every single house. And there's studies of the World Bank that say that even if every household was connected to the grid, more than 50% couldn't even afford it to pay for it. So you really have to kind of rethink the way you approach the problem. In the end, we hope to really scale it up, because it's not just about Rwanda, but rather we want to develop a versatile solution that can be replicated on a large scale to really achieve impact and to change people's lives.
Christopher Hopper, chairman of Equinox at Imperial College London, explaining how energy kiosks could help provide power to rural areas of Africa.
What an amazing story. It's Chris Smith and Diana O'Carroll with you on this week's Naked Scientists. If you'd like to get in touch, you can tweet at Naked Scientists, or why not send us an email, chris@thenakedscientist.com. Still to come, we'll be finding out about an exciting way of storing energy at minus 160 degrees Celsius. Now, as we've just heard, though, small-scale turbines that can harness energy locally from winds, tides and rivers can be a very valuable asset in bringing power to remote populations, which makes the technology that a company called Green Tide Turbines are working on potentially very valuable. Mira and Dave went to meet Green Tide Turbines CEO, Michael Evans, and his colleagues to find out a little bit more.
Well, if we're talking about a tidal turbine, we're developing in technologies that have to survive some of the most aggressive environments in the whole planet. We've got heavy moving water, which contains huge amounts of energy, often in very remote locations, which are very hard to access because obviously you've got these very strong tidal currents and also some extremely large forces, which is the whole reason why we want to put turbines there, to tap some of that. So the emphasis really needs to be on devices that are really, really simple, very easy to maintain, very robust, and also quite cheap.
I guess the default thing to do would be to take a known technology, like take a wind turbine and stuff it underwater.
Absolutely. A lot of our competitors have followed that very, very philosophy. Basically, they've just got wind turbines with shorter blades that are made to be waterproof, and they dump them under the sea. And the sea just isn't water. There's lots of stuff that it carries in it. Things like fishing nets, even submerged containers that have been washed off ships, for instance. These all sort of find their way into these fast-moving flows of water and are basically flung at these devices. So you've got these wind turbines with their delicate blades spinning around in this sort of flow regime. When these things get hit by these objects, they're not going to survive particularly well.
To tell us more about how the Green Tide turbine design approaches these challenges is Tom Clark, who's the research director.
Well, we have a different kind of concept, which is moving away from the wind turbines underneath the sea. What we do is we put much smaller rotors inside a duct, which allows us to capture a similar amount of energy, but using a much smaller and more robust rotor.
I guess the first thing I'd say, if you've got a very small rotor and you're sort of squirting lots of water past it, surely everything's moving very fast. This turbine should be spinning very quickly and kind of mash anything which it hits.
That's right, but what we've been able to do, Dave, is use both a stator and a rotor. So a stator is essentially like a rotating turbine, but fixed in position. What that does is it causes a swirl of fluid inside the duct, and then the rotor takes out that swirl and generates energy by doing so. So, although the rotor is moving fairly fast, it's not moving as quickly as perhaps a design without a stator.
So you're regulating really the flow of water approaching the rotor?
That's right. That has the additional benefit, actually, that any turbulence and gustiness in the incoming stream is actually straightened and aligned as well. A lot of people don't realise it, but the tides don't move just uniformly. There's a lot of turbulence, swirling eddies and so on, and currents, which upset the behaviour of turbines in the current. Benefit of our design really is that you can actually stack our turbines closer together in a tidal farm than with open type turbine designs.
So your system is causing the water to spin, and then you're changing the direction of that spinning water completely using your rotor. So because you change the direction a lot, you don't need to be moving the rotor as quickly.
That's right, yes. Because we have swirling motion in the inside of our duct, our rotor can be moving much more slowly. Effectively, it moves with the water. So there's less of a relative speed between the water and the rotor. So it's much less damaging for fish, and it's much less likely to get debris and other objects caught in the flow through the turbine.
Well, now you mentioned that they can be situated quite close to each other, but what are the actual dimensions of the turbines?
Our tidal turbines are in general in the range of 10 to 15 metres in outside diameter. But the ducts are quite big, so the rotors are actually substantially smaller than that, of the order 6 metres.
We're at one of your test sites now. We're just alongside a river, and you've got a tunnel through which water's flowing through. It's about 1.5 metres to 2 metres wide, and you've got one of your turbines just placed in the middle. It's about 1 foot wide in diameter. Tell me a bit more about how this setup works, though.
Well, it's called a Venturi arrangement. Essentially, there's a nozzle which accelerates flow into our turbine for the purposes of testing, because we need a higher flow rate to accurately test the turbine. So the flow rates that we reach in the test section of our water tunnel are around about 2 metres per second. The action of the duct around the turbine actually accelerates fluid through the turbine disc, which means that the velocity inside the duct is slightly higher than the mean flow rate. It's about 2.5 or 3 metres per second. We have part of the flow of a river diverted through our test facility. We can control the facility, we can control the flow rate of the river using a sluice gate up in front of our turbine.
Can we see it in action then?
You certainly can. All we need to do is open up the sluice gates.
Right, so the sluice gates are open and the water is now just flooding through.
That's right. Well, flowing through the tunnel is about 3 cubic metres per second of water. We've got water travelling up to 2 metres per second.
Going through then the turbine, how much power will be being generated here?
Well, that corresponds to a power of about 500 watts, which really isn't very much. That's about half a household kettle. But I should say that it's a very, very small model that we're using. The energy capture scales up dramatically as you increase the diameter up to our tidal turbine scale. Our commercial scale turbines typically produce around 1 megawatt of power, which is useful. I think that generates enough power for about 300 homes.
Having seen it in action then now, moving back to you, Michael, where is it hoped these turbines will be used? What are the upcoming projects then?
Well, we've had a great deal of interest from developing countries where there's lots of rural communities well away from established infrastructure needing power, and relatively small amounts of power, generating power for lighting, for running mobile communication systems and things like that. One country in particular who's very keen on our technology is Brazil. So these will be on a scale of about 1 metre in diameter, installed in probably northern Amazon region initially. They'll be generating around about 5 kilowatts of energy.
I guess even if you're going to put diesel generators up there, you still have to ship the diesel up there regularly, so it's even less hassle than that.
Absolutely, and on top of that, you've got a lot of enthusiasm for clean technologies, and other alternatives such as photovoltaics and wind wouldn't really work in a rainforest type environment where obviously you've got lots of clouds most of the day, and also with the trees there's not very much wind at a usable sort of level. So a river generation technology is ideal for this sort of environment.
So although you started off building a tidal turbine, you've ended up putting it in rivers instead?
Making smaller turbines is a lot cheaper, obviously, and we need to prove our technology. The river turbine is a fantastic test bed to actually develop the technology.
What an amazing breakthrough. That's Green Tide Turbines' Michael Evans, and before him, Tom Clark, and they were talking to Dave and Mira for this week's Naked Engineering. And if you'd like to find out a little bit more about that technology they were discussing and how it works, there's a wonderful video, including a wonderful bit of Dave Ansell animation, and that's on our website. You can see that video at nakedscientist.com/engineering.
This is The Naked Scientists with Chris Smith and Diana O'Carroll. We're talking this week about new ways to generate, distribute and store energy. Also still to come is my question of the week, where I'll be finding out if you can drink through your bottom.
Yes, but not your bottom. Just joking. Now, one of the outstanding problems in energy provision is how to store it in such a way that the energy can be accessed rapidly and efficiently on demand, in other words, when you want it. But now a Cambridge-based company called Isentropic has developed a cutting-edge solution using gravel pits as enormous batteries where they store energy thermally. And to explain how it works, Technical Director Jonathan Howes is with us. Hello, Jonathan.
Hello, Chris.
So, first of all, Jonathan, tell us what actually is the problem that you're grappling with here?
Well, this came about as a result of some thinking I was doing in the mid to late 1990s, when, like many engineers, I was quite keen on clean power generation methods. The more I looked at it, though, the more I realised we were actually trying to solve the wrong problem, because there were plenty of people working on clean tech ways of making power. But the big problem with all of these is they're either very, very inflexible, like, for example, nuclear, or they're extremely erratic, such as wind or solar. Tidal is less erratic, but it still comes and goes with the tides, inevitably. So the more important problem to solve was to buffer energy so that the intermittency problem or the inflexibility of nuclear would then go away. And this would actually enable the widespread adoption of these other technologies. The real concern for me was always sustainability rather than clean tech, because sustainability is, the opposite of sustainability is unsustainability, which is self-evidently a silly way to go. So this struck me as being the bigger problem. In solving the issues of making sustainability achievable, you inevitably end up cleaning power supplies anyway, because sustainable, almost by definition, means clean.
And obviously, to put this into perspective and to give an everyday context to it, one of the big problems that power supply companies grapple with is EastEnders finishes or some other hot programme finishes. Everyone gets up, whips on the kettle, turns the boiler and the lights on and so on, and there's a big surge. And you've got to have capacity there to cope with that, and that means you've got to run stations at beyond demand in order to have the spare capacity in the system to meet that demand.
Yes, this is the load levelling problem, which is a definition of the short-term storage issue. There are two storage problems, primary storage problems. One is long-term or seasonal storage, perhaps storing energy during the summer when it's plentiful for use in the winter. The other one is the short-term load levelling issue, as you've just described, for local peaks and troughs in demand.
So tell us about Isentropic's solution then. What are you doing and how does it work?
Okay, what we're doing, this is a thermodynamic approach. If you consider a heat engine, as you'll find under the bonnet of a car, it produces a temperature difference, usually by burning a fuel. They don't have to do it by burning a fuel. You can use solar energy to create the temperature difference. That temperature difference then passes through a device and produces mechanical power. Now, there's an opposite of this called a heat pump, which is again well known, but I think perhaps it's not quite so widely appreciated that heat pumps are the exact inverse of an engine. And a heat pump takes mechanical power through the shaft and converts it into a temperature difference by pumping heat from one place to another. If you can make a heat pump sufficiently reversible, thermodynamically reversible, you have the possibility of using it to pump heat from one volume of thermal mass to another volume of thermal mass, and then allowing it to discharge back through a similar or the same device back to its original state, and then releasing the power that was used to create the temperature difference.
So, to explain practically how this might work, I would consume electricity from the grid. I would use this to do some work moving something from one place to another place where there'll be a temperature difference, which I can store. And then, when I want the energy back, I can move the thing from the place where it's at one temperature to the other temperature, getting the energy that I used in the process back out at some degree of loss. Obviously, there's no such thing as 100% efficiency yet. No. And that means that then you've stored the energy somewhere until such time as you need it, but you can recover it from that thermal difference.
That's exactly correct. It's an exact analogy exactly analogous to pumped hydro, where water is pumped from one level in one lake to another lake, and then it's consuming energy and then allowed to flow back down again through a turbine to release the energy again. Where they pump water up and down a hill, so altitude represents temperature, we pump heat up a thermal hill to a high temperature reservoir.
And what are you heating up and what are you cooling down to make your thermal difference?
We have an engine circuit which runs an inert gas, namely argon, through a compression and expansion process. If argon is compressed, then, or any gas is compressed, the temperature rises. Having raised the temperature of the gas is then passed through a particulate store, a mineral particulate store, which in its simplest form could be regarded as gravel, although of course you could use a ceramic or something more sophisticated. There's every reason not to for reasons of cost. It leaves the heat behind in the particulate, so it now cools back down to its original temperature but remains at the higher pressure. If you then expand it back to its original pressure, then the temperature now falls to significantly below ambient, and it's passed through another store, leaving the cold behind in that store. If the heat exchange takes place efficiently and slowly, it can be highly reversible. If the compression and the expansion take place in very, very well-designed, insulated spaces at high speed, that can also be highly reversible. So what we do is string 4 highly reversible processes together. So we can now run it backwards as an engine, allowing the heat to run back through the machine, releasing the mechanical power to drive a generator to get the electricity back again.
What sort of efficiency can you manage?
Okay, round-trip efficiencies. Based on our earliest testing, we estimated with fairly cautious assumptions that we could achieve about 72%. With more realistic assumptions, we're in the range of about 75 to 80%.
And in terms of space, how would this compare with the example you gave earlier, which is pumping water from a low-lying lake to a higher-lying lake so that you can then recover that energy by running the water back down through turbines later? How much energy can they make and how much space do they take up compared with you?
They are typically fairly sizable plants because if you've got a suitable mountain range or a range of hills and an appropriate valley to use, it tends to get used to the limits. So they tend to be quite large capacity plants. Now, Bath County in Virginia in the USA, for example, has a 30 gigawatt storage capacity. If we did our equipment with the same 30 gigawatt hour capacity, it would consume approximately 1/300th of the land area. Another way of looking at it, we spec'd out a prototype utility scale machine of 2 megawatts power capacity and 16 megawatt hours storage capability. That consumes a footprint of about 8 metres by 16 metres by about 7 metres high.
So very, very small and efficient. And just in 20 seconds, Jonathan, you've got the prototypes running, but when can we see this plugging into the grid and giving us the surge capacity and long-term storage that we need for the future?
We are initiating the design of a utility storage demonstrator prototype, which is going to take around about 2 to 2.5 years.
Terrific. Thank you very much. That's Jonathan Howes. He is from Isentropic, which is a local company who are pioneering a new way to store and control and distribute the release of energy. And this is The Naked Scientists with Chris Smith and with Diana O'Carroll.
I've got a question here for both you, Chris, and Jonathan. It's from Appman1970, and he says, could you dangle a tether down from space and generate electricity from that, or could you drill deep into the crust and harness thermal energy?
Well, let me do the first bit first, and then Jonathan maybe can talk about the temperature bit, because that's more his bag. You could dangle a wire from space. If you had a satellite on a very long cable, you would have a wire which was passing, if the satellite's orbiting, through a changing magnetic field, and if you do that, you will induce a current in the cable, and therefore you will separate charges in the cable, and you have a plus end and a minus end. That's true. But how do you get the energy out? Because you've then got to pass another wire from the plus end, or all the charges, to the minus end to get a circuit, which means you'll have another wire passing through exactly the same magnetic field, and it's going to get exactly the same charge separation, so there'll be no net gain. Nice idea, probably very difficult in practice. Jonathan, what do you think about the geothermal part of the question?
Well, of course, Geothermal energy is very, very widely used, particularly in countries which are geothermally active, like New Zealand. I think the question, though, is referring to digging very deep indeed into the Earth's core. This would be incredibly expensive. Deep drilling, going down maybe 1,000 feet is achievable, but it's not cheap and not particularly easy to steer. So geothermal tends to be restricted to areas where suitable geothermal conditions occur, where heat comes close to the surface and can be tapped.
Another quick question for you, Chris. It's from Corey Albrecht, and he says, is wireless transmission of electricity possible? And there's also an email from Paul Kuhlman, who says a Californian outfit has patented the rights to produce electricity from the sun and transport it to the earth by high energy beams, but would there be deadly areas where they beam it down?
Yes, I looked up which company that was. It's Solar and Space, who are a Californian-based company. Sounds intriguing, actually. They've got permission to develop this system. They want to have a satellite array out in space at about 22,000 miles out, and this would have very big photoelectric cells that would harness solar energy, turn that into electricity, which they then convert into a microwave beam. They then beam that microwave energy down to the Earth to a very big collecting dish. And their argument is the collecting dish would be about a 2 square mile across array. So very, very big. So the energy density of the microwave beam coming in from space would be quite low. And actually, they say if an aeroplane were to fly into that, actually the amount of heating effect the aeroplane would feel from the microwaves would be less than the heating effect of an aeroplane just coming out from under a cloud and being hit by sunlight. So they say that this is not a threat to birds, planes, cars, people, or anything. And the idea is they then sum all of that energy collected by the dish back together, and this could generate, as they say, energy at the rate of 200 megawatts, which is not small, but it's also not huge either. But this is just early days. The Japanese aerospace exploration industry say they're also planning something similar.
Well, that's a shame. It could have at least guaranteed that your in-flight meal would be warm, but anyway.
I don't think we can quite stretch to that. Anyway, Diana, thank you. Well, look, you've asked me some hard questions. Now it's your turn to go under the spotlight.
Yes, well, this week, after struggling to find the right experts in the field, it almost ended on a bum note.
Hi, my name is Rob, and my question is, given that people can absorb medication in the form of suppositories, is it possible to absorb enough water to survive through their bottom?
So, what goes on in the colon most of the time? Here's Miles Parks.
Using the rectum as a means of administering fluid replacement in dehydrated individuals is an interesting idea. The colon or large bowel, of course, functions primarily to absorb fluid, normally doing so, of course, as material enters to the cecum from the small intestine, the material which has not been digested, fibrous products and so on, together with a substantial amount of fluid and solute, enters into the colon, and the fluid is then sucked out as the material goes round the 4 feet or so of the colon to form up the stool. So you can see the colon is well designed for absorbing liquid, but it really needs to do so in the context also of transport of solute, that's to say of sodium and chloride ions and so on, and it's the absorption of the solute itself which then creates the osmotic gradient which sucks fluid across the lining of the bowel and into the bloodstream. So, bearing these things in mind, I do think that water enemas on their own, water on its own, is perhaps unlikely to be absorbed in clinically significant quantities, and of course it's just likely to come out of the rectum again, whereas I think administering saline or something of that type would potentially lead to quite significant absorption of fluid.
Miles Parks there, gastroenterologist at Addenbrooke's Hospital. Water on its own probably wouldn't do very much, but a saline solution could give one a better chance of a drink. But what if you're stuck for saline drips and all you've got is the much saltier seawater?
My name is Ari Urkel, and I'm an intensive care doctor and physicist from the University of Cambridge. Unfortunately, giving yourself a seawater enema for hydration if you've had the misfortune to be stranded at sea is a complete thermodynamic non-starter. The problem is that the salt in seawater is much more concentrated than the concentration of all the various solutes found in body tissues. Since, to a first approximation at least, the gut can be thought of as a sort of semi-permeable membrane, this will lead to water molecules tending to move from the body through the gut wall and into the seawater to reduce the concentration difference. This process, where water moves along its own concentration gradient across a semi-permeable membrane, is called osmosis and is very important in biology. In this case, it will actually result in you becoming increasingly dehydrated. The situation is reversed with fresh water, which would be successfully absorbed. Having said that, neither procedure would be very safe, especially if the water was dirty. So, giving yourself a seawater enema if you're trapped at sea is likely to make you lose water. Of course, giving yourself a seawater enema if you're trapped at a cocktail party is likely to make you lose friends as well.
So it's not recommended that one inserts liquid into one's derriere. But if you were in need of a drink, then a slightly saline solution would probably do the trick. Salt water is too salty and normal water is too watery. It turns out that this version of the saline drip was used heavily by medics of the past and is still used in some cases today. It's known as proctoclysis. Next week, we've another health-related intervention.
Hi, Naked Scientist. It's Alan Blake from London. I have a question for you, please. I received a brochure from a company called Magnetic Therapy Limited advertising all things magnetic and claiming to cure all sorts of ailments like snoring if this object was put up the nostrils and all sorts of aches and pains if worn on different parts of the body. Please can you advise me if there is any evidence at all to prove that magnets have these type of powers, and if so, how they work? Thank you.
What's the truth behind these contraptions? And since blood is full of iron, can it be magnetic? Answers to Chris at thenakedscientists.com or write them on the forum, and that's at thenakedscientists.com/forum.
Thank you very much, Diana. Well, that's pretty much it. We have run out of time, I'm afraid. Very quick question from Nat Spirit in Second Life. He wondered, is it less windy behind wind farms? Well, the answer is yes, because the wind farm has extracted energy from the prevailing wind in order to turn it into electricity. So by definition, it must have taken some momentum out of the air, and therefore it's less windy. Our thanks to our guests this week, Paul Davis and Jonathan Howes, and also our wonderful production team, Tom Simpkins, Ben Valsler, Miracentha Lingam, Dave Ansell and Diana O'Carroll. My name's Chris Smith, and we'll be back next week with a look at graphene, the stuff that won a Nobel Prize for a number of physicists this year and holds the key, potentially, to big, flexible screens for your computers and also the replacement for silicon PC chips in the future. If you've got any questions, send them in. Chris at nakedscientists.com.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at nakedscientists.com.